Welcome back, everyone. Let's go over the SPSS Independent Samples T-Test assignment. So this is from back when I lived in downtown Sac, and I had a sort of a gripe against the parking people because I couldn't sleep in on weekends. So I started making mean problems about them for my stats class. So, the chief of the parking ticket patrol for City of Sacramento is a sadist who is curious about whether the daily application of random electric shocks to parking ticket writers would change the number of tickets that they write in a week. Half of the city's 24 ticket writers are randomly assigned to wear an armband that delivers random electric shocks during the workday. The other half are randomly assigned to wear an armband that does not deliver electric shocks. Given that each of the 24 ticket writers was independently and randomly assigned to one of two shock groups, X1 shocked and X2 is not shocked, this study has a between subjects design. At the end of the week, total number of tickets written by the 24 ticket writers is calculated and is shown in the table below. They're in a data file. Download this file. And here's the research hypothesis. Does the average number of tickets written differ between shocked and not shocked ticket writers? So, I guess question number one, this hypothesis, is it one-tailed or is it two-tailed? So, two-tailed one is like, hey, this will have some sort of effect. There will be a difference of some sort. A one-tailed one would say those who are shocked will write more tickets, or those who are shocked will write less tickets. It picks a direction. So in this case, we have a two-tailed hypothesis. So two-tailed hypotheses, as shown here, are always written the same sort of way. Your null is that there is no difference between the groups. The alternative is that there is some sort of difference between the groups. So that's what we write. So our null is that they are equal. The two means for shocked and non-shocked ticket writers are equal. The alternative is that they are not equal. So now we're going to check the normality assumption for independent samples T. We're going to do this by getting the skewness coefficient. We need it for each group because remember, it's that the scores are approximately normal in each of the groups. And so to do that, we're going to use explore. So that's over in SPSS under Analyze, Descriptive Statistics, and Explore. And explore is the descriptive statistics procedure that will actually do things for subgroups. It's from like, I don't know, week 3 of class, something like that. So our dependent variables tickets written, shock condition is our factor. Under statistics, we can kind of see what we're going to get. Whatever's in here, that's what we're going to get. And if you want to cut down on output, you could just click statistics. I don't tell you guys to do that, so just click OK. Let's take a look at what we get. So remember, the skewness statistic is what we use to determine the shapes of things. And so this is for shocked persons and not shocked persons. You get lots of stats, but in there is skewness. Scooting on over, we get negative 0.246. So remember back to the rule here. The rule is as long as a skewness statistic isn't an absolute value of 2 or bigger, it's basically normal. So in this case, we would say, well, first of all, the question is, what's the skewness statistic? It's negative 0.246 right there. And then for the other group, for not shocked persons, skewness is 0.283. These aren't perfectly normal, but they're normal enough. So 0.283. Do these data meet the normality assumption? That is either of these things have an absolute value of 2 or bigger? No. So we would say, yeah, the normality assumption is met. These things are, for all intents and purposes, normal enough for us to conclude that. So now we're going to, excuse me, actually run the independent samples t-test. That's under Analyze, Compare Means and Proportions, and Independent Samples T. 2 boxes in here. We got to put stuff in. Test variable is what they call dependent variable here. So we got to put tickets written in there. Grouping variable is what they mean for independent variables. So we put shock condition there. Note the 2 question marks. It's asking you what groups to compare, what numbers represent those groups. And if you go way up to the top, you can see 1 was shocked, 2 was not shocked. So we have to click it define groups. It auto fills in 1 and 2, which is kind of cool. So we don't have to type 1 and 2. It auto fills those in. Let's check options. Nothing under here we care about. Just click OK and you get your independent samples t-test. So I will scooch this over so we can see things a little bit better. All right, what is the mean and standard deviation for each level of the independent variable, round to 2 decimals for shock ticket riders? The mean is 158.42. The standard deviation is 25.02. For our shock ticket riders, the mean is 128.25, standard deviation of 23.58. So using alpha of 0.05, do the data meet the normality assumption? So down here in the independent samples t-test table, and this is one of those ones where I'm like, flip this thing sideways when you export it because it goes off the page, right? It's a really long table. But what we do is we look, there's a section in here that's called Levine's test for equality of variances. We go down to SIG in here. We look at SIG, and if SIG is greater than 0.05, we have met the assumption. If SIG is less than 0.05, we have violated the assumption. And then based on which, whether we can assume equal variances or not, we interpret one or the other line of the t-test result. So it's kind of like a signpost. SIG here is greater than 0.05. So because it's greater than 0.05, we have met the assumption. The answer is yes, we have met it. So which line of t-test results should we actually use? Well, we should use equal variances assumed because we did not violate the homogeneous or equal variances assumption. So then we scoot over to our significances, and you've got to choose one-tailed or two-tailed. We have a two-tailed hypothesis. So, let me scoot Sean down. So we have to determine, is this less than 0.05? Yes. 0.006 is less than 0.05. So do they mean significantly different from each other? Yes. Are we able to fully reject the null hypothesis? Well, what's required to fully reject a two-tailed hypothesis? The only requirement is that two-tailed SIG is less than 0.05. So yes, we can reject the hypothesis. So what's that mean? It means there is a significant difference between these two means right here, 158 and 128. That is not a chance difference. So why or why not? Well, for equal variances assumed, the SIG two-tailed was less than 0.05. So that is our why or why not. So what is the mean difference between the groups? Two ways to do this. One is just do some subtraction, 158 minus 128, and change. The other thing is out here, it actually gives you mean difference, 30.17 when you round it, so 30.17. Which group had the higher mean? Well, let's see, it's the 158. 158 versus 128, it was shock ticket riders. So shock ticket riders. And then what proportion of variability is accounted for by the independent variable in the dependent variable? This is where we got to do omega squared, or this little guy right here. So I was seeing real quick if the effect size actually matches. They do not give you omega squared over here. So this is one of those ones where the effect size is useless. Give you Cohen's d, which is another effect size that's commonly used, but it's not the one we need for this. So we're going to have to calculate this sucker. There's the formula. So what we have to do is calculate the top and the bottom. And so let me grab a piece of paper because we're going to have to write this stuff down. So on the top, we got the t value, and we square it, and we minus 1. So that is 3.039. Let me get calculator going. 3.039. That's our t value right there. We square it. Then we subtract 1. Minus 1 is 8.2355, etc. So that is the top of this equation. The bottom of the equation is t squared. So let's put that in again. Same t, 3.039 is our t value. We square it. But what we do is we add the sample size of group 1, the sample size of group 2, and then we subtract 2. So sample size of groups are up here. So we'll do plus 12 plus, right there, the other sample size, 12, and then minus 2. You get on the bottom of this thing 31.2355. So I'm going to go back to what's on top, which was 8.2355. That was the t squared minus 1, divided by the bottom, which we said was 31.2355. And we get 0.2636, etc. Rounding this to two decimals, we'd say 0.26. 0.26 is the answer. So that is our omega squared. 20, if you turn that note to a percent, 26% of the variability in ticket writing could be accounted for by whether or not they were shocked, the independent variable. So now we got to fill in our actual t value. So we have a t with 22 degrees of freedom is equal to 3.04, 3.04. Our sig was less than 0.05, so we do less than 0.05. And omega squared, we just calculated here, is 0.26. Interpret the meaning of the results. This is the what would you tell grandma? So what do they tell us about whether, and if so, how the independent variable affected or was associated with differences in the dependent variable? Well, what we've done here is we've compared mean ticket writers for these groups. We determined that there's a significant difference between them. And in fact, shock ticket writers wrote more tickets on average, about 30 on average, compared to not shocked ticket writers. So that's the answer is shock ticket writers wrote 30.17, if you want to get crazy, more tickets on average than non-shock ticket writers. If the data had been ordinal or severely violated the homogeneity variances assumption, or the sample sizes were very small or unequal, what backup test could you use instead? So I'm asking you for the weed whacker equivalent that you can do if you violate the assumptions for independent t. And if indeed you go to your matrix of statistical tests, which I got to dig out from somewhere. What week was that? This one, I think. Answer key. Nope, nope, nope. Where is my matrix O statistical test? There it is. There's our handout. Let's pull it up. The secret here is you just look in the row above the test you're doing. So we're doing independent samples t-test. The one above it is Mann-Whitney U-test. The answer is indeed, boom, Mann-Whitney U-test. That's your backup. So hopefully this made sense. And don't forget to do your APA write-up using the APA template that is also up in the assignment. That's it.